ChatGPT solves dark matter. Hello, my name is Franklin Hu, and in this presentation, we're going to be explaining how ChatGPT solved the dark matter problem as a case of mistaken identity for gravity. In this presentation, we'll first be covering what is dark matter. And this simply means that the galaxies don't behave the way we expect. Secondly, we'll be covering what's the matter. And I believe this is due to the fact that we are using the wrong formula for gravity. Next, we'll be looking into some problems with galaxies which are literally missing their dark matter. And this rules out both dark matter and modified gravity explanations. Finally, we will be getting to ChatGPT to see whether it can rescue us and explain what is going on with dark matter. So first, what is dark matter? So dark matter is proposed to explain galaxy rotation curves. So I have a picture here of a galaxy rotation curve for the M33 object, and this is showing the velocity of the stars as you go out further in the galaxy. And from this picture, we can see it is observed that the speeds of the stars just steadily increase. Even way out here in the outskirts, it's going much faster than on the inside. However, this contradicts standard gravitational analysis, which would predict that the stars in the outer region should be slowing down. So this is based on the gravity law, which is gm over r squared, and this drops off as the distances increases. So we're very familiar with, say, the solar system, where the planets which are further out orbit much slower than the ones closer to the sun. For example, the planet Mercury orbits much faster than, say, the planet Venus. Now, in order to account for this not slowing down, it is proposed that there's additional matter that we cannot see, which is enabling the stars in the outer region to rotate as fast as we see. Now, we call this dark matter because we don't know what it is, and so far we haven't detected it. So dark is kind of literally not meaning that it's like black, but that we really don't understand what it is. It's like we don't know. We should call it we don't know matter, really. So, but what could possibly be the problem here? Now, these galaxy curves that I showed you are calculated using the standard gravitational formula, which you should have all seen, which is force is equal to the gravitational constant times the product of the masses divided by the radius squared. So that seems to be very straightforward. However, the original form of the universal gravitational law really is that the force of gravity is proportional to the mass of the objects divided by the distance from the centers. Now, you'll probably think, well, there's no difference between those two, but there is a very significant difference. And that the significant difference is the term radius. You see we have r, which is radius, versus distance. Distance does not imply anything circular or spherical, such as a r squared. I mean, the actual general form of the universal gravitation law should have this as d squared, not r squared. Now, to demonstrate that there is something definitely messed up about this formula, let's suppose you try to use this to calculate the gravity at the center of the Earth, for example. So in that case, so the radius would go to 0, and what happens? Well, the force would go to infinity because this large number divided by 0 is infinite. And that can't be true. Intuitively, we would think that if you were in the center of the Earth, because all the forces would be pulling away from you, that really the force should be zero. But it's not. So since that's completely wrong, then this cannot be the general form of the gravitational law. So I would say that this is really a case of mistaken identity. This particular formula, which seems completely innocuous, does not actually express the law of universal gravitation. It is actually a very complex simplification derived from shell theorem. Now, that is something that Newton invented. And in shell theorem, what that says is that a spherically symmetric body affects external objects gravitationally as if all its mass were concentrated at a point at the center. Also, if the body is spherically symmetric, no net gravitational force is exerted by the shell on any object inside, regardless of the object location within the shell. So we can basically ignore anything which exists outside the radius we're looking at. But strictly speaking, this only applies to spherically symmetric bodies. And specifically, it does not apply to flat disk-shaped galaxies. For example, if the Earth were shaped like anything other than a sphere, let's say a rectangular bar or a pyramid or just some weird looking blob, you could not apply this formula simply because those shapes have no radius that you could be applied to. Now, to further explain this, Newton had to actually derive this based on the problem of trying to calculate the force of gravity on a mass sitting on the surface. So this would be like I'm sitting in a chair and I'm sitting on the earth. So what is the force of gravity on me? And the only way to do that is to sum up all of the forces from all of the rocks in the earth. Now, it may not be particularly obvious, but the universal gravitation law, applies to relatively small point masses like that you might find in, say, a Cavendish experiment, like a small round ball against another small round ball. But when the Earth, we have one gigantic ball and then one tiny little human, and the distance between the human and the ground initially right beneath me is zero. And so how do we calculate the force? Because the force is the sum of like the block of earth that's right beneath my feet added to the force of the earth on the block of earth that's in China and all the other blocks in between. Really, the only way to adequately calculate this is to break the earth into blocks and calculate the force from each block to the mass sitting on the surface, which would seem to be an impossibly complex task. But yet this is the task that Newton set about to solve. Now, the way that this is done is extremely complex. The derivation here, this is a little piece of the derivation. And I can only kind of describe it by, if you imagine that you broke the earth into like 1 cubic yard blocks. Okay, so I can calculate the force of gravity on the 1 cubic yard of earth that's directly beneath me against, say, my body mass. Then what I could do is that I could take the next cubic block of dirt in front of me and calculate, that's a little bit further away, what the force of gravity that block is. And then I could do the next block in front of me, and the next block in front of me, and the next block in front of me, until you would have to go all the way around the earth in a ring. And at that point, then you could calculate the force of gravity of like a 1 yard deep ring of earth all the way around the earth to me for that ring. Now, then you can go down 1 yard deeper and you can repeat the process. Another ring, just 2 yards down, all the way around. then you could just keep on going until you got all the way down to the center of the Earth. Then you could describe the force of gravity of the disk of Earth that is sitting right beneath me. Phew! Now, to get the sphere, then we could go to my right, go 1 yard to my right, and repeat that entire process. So I get another disk that's to my right. And then I could keep on building all these disks until I got like half a sphere built up. Then, obviously, I would go to my left and I would do the same thing and build up a bunch of disks until I got a whole sphere on my left. And actually, calculus was invented by Newton as a result, because due to the spherical symmetry, we can write equations that can, generally speaking, add up what the sum of all of these blocks are. Now, it's not at all obvious what the answer should be. If I'm sitting on the Earth and I'm 160 pounds and the Earth weighs whatever it does, what is the force that's going to be on me as a result? Well, the surprising result is that the formula that you end up with looks absolutely identical to the original gravitational law. Here it is, E equals gm over p squared. Boy, how frustrated Newton must have been to go through all of this work to invent calculus and add up all these blocks and spheres and disks and just to come up with a formula which looks exactly identical to the one he started with. So what proof do we have? Now, this particular formula only applies to spherical symmetric bodies. Once again, if you went back and looked at the full derivation of shell theorem, I think you could easily convince yourself that this only applies to spheres and only applies to the area outside of the sphere. So how would we possibly prove that this doesn't work for disk-shaped galaxies and that this is actually the root of the dark matter problem? Because we're using a formula which only works on spherical distributions. Well, one way we can do this is that we can look at galaxies which are actually spherically symmetric to see if they do obey this law. And the prediction would be is that these spherically symmetric galaxies would be the only galaxies for which this formula would work correctly, and we should see that there should be no dark matter, there shouldn't be any anomalous galaxy rotation curves. It should follow exactly this r² gravity. And this was first proposed by David de Hilster in his paper, beyondmainstream.org, galaxy geometry reveals no need for dark matter. And in this paper, it showed that galaxies which are spherically symmetric do not exhibit any dark matter anomaly, because these are the only galaxy shapes in which the symmetric gravity law applies. So there is also a rather lengthy video showing how just regular Newtonian gravity, if you apply it correctly, actually explains the galactic rotation curves without the use of dark matter. So if we have a sphere, then if we use what I'm calling the spherical gravity law based on spherical distributions, then we get a correct prediction for these spherical galaxies. However, we would predict that if it's not a sphere, like your typical flat disk galaxy here, that the one over r² formula is simply wrong, and that we would predict that it should not match. So this particular hypothesis that we're just simply using the wrong form of the gravity formula, this makes the very strong prediction that no dark matter will ever be found in a spherically symmetric galaxy. And so I assert that this proves that the mainstream has been using the spherical gravity law incorrectly on disk-shaped galaxies. Now, this problem with galaxies missing dark matter is quite problematic for the whole dark matter hypothesis. So, in fact, this paper here has 6 examples of galaxies which have no dark matter. Now, maybe one of them you might be able to explain, like this one. They're saying, due to tidal forces, the dark matter has essentially been washed out of the galaxy. Okay, well, maybe one, but 6? It's not terribly likely. And you can find pictures of these 6 galaxies in this reference here. And, I'm no expert, but, just looking at the pictures that have been provided here, yeah, these do not look like flat disk galaxies. These look like spherical, round galaxies. Now, the problem with this is that galaxies with no dark matter pretty much rule out all existing explanations, including the other favorite, which is modified gravity. Because, the problem with modified gravity is that all galaxies should have dark matter in them if gravity simply changes a bit depending on the distances, which is modified gravity's main assertion. But we have these galaxies have no dark matter, and therefore, how would modified gravity know when to turn on and off? It simply cannot. And even the researchers who, looked at these missing dark matter galaxies really don't have any suitable explanations. As in this quote, as Pina and his colleagues indicate in their study, there are several possible explanations for the lack of dark matter. For starters, AGC 114905 may have been stripped of its dark matter through tidal interaction with neighboring large galaxies. They also adjusted the parameters of lambda cold dark matter, cosmological model, and alternate theories to general relativity to obtain values consistent with their observation, but as Pina explained, none of it worked. None. But there are none, and in the most reputed galaxy formation framework, the so-called cold dark matter model, we would have to introduce extreme parameter values that are far beyond the usual range. Also, with modified Newtonian dynamics and alternative theory to cold dark matter, we cannot reproduce the motions of gas within the galaxy. So these 6 galaxies which have no dark matter at all are throwing a ginormous monkey wrench into all the existing explanations for dark matter. However, the one thing that they all have in common is that they're not flat disks. They appear to be spherically symmetric, which leaves the only alternative is that the spherical gravity law has been incorrectly applied to disk galaxies, which is the main hypothesis of this presentation. So, finally, we get to ChatGPT, in case you were thinking the title of this presentation was clickbait. So, if the spherical gravitational law doesn't apply to disk galaxies, then what gravitational law applies to it? Well, we have artificial intelligence and we have ChatGPT. We can simply ask it, what should the galactic rotation curves be? And so I asked it a series of questions, leading questions, and it came up with because I first asked it to calculate what would it be for a completely flat and constant density disk galaxy. Then I asked it, let's change it so that the mass density decreases exponentially with radius, which is more realistic. And it came up with a very complicated formula, and ultimately it produced, amazingly, this Python code, which would produce a plot of what it thought the expected gravitational well, the expected galactic rotation curves would be. And what did it plot? Ta-da! ChatGPT produces a flat curve which matches generally what we're observing in most galaxies. So there you have it. ChatGPT solved the dark matter problem by showing the flat rotation curve can be obtained with just straight calculations and not using dark matter. How about that? Of course, the question is ChatGPT just being insane? Artificial intelligence is great, but it has been known to just make up stuff from time to time, and anything it comes up with should be taken with a liberal grain of salt. Okay, so maybe it's screwed up. But really, no matter how ChatGPT came up with this conclusion, somehow it produced the correct result that matches actual observations. So, how did it do that? Did it do it accidentally? But even accidents in science can produce unexpectedly useful results that end up advancing our knowledge, right? So it did something, it came up with the right result. And even looking at what the program did and the original equation it presented, I would say that, yeah, it made a mistake because this particular formula here is like missing the divide by r term quite significantly. And that r term comes from the 1 over r squared assumption of spherical gravity law. So somehow I fooled ChatGPT into forgetting about the spherical gravity law. But really, what is ChatGPT's mistake telling us? Because, yeah, it got the correct result of a flat gravitational curve. I mean, that is the right answer. That matches what we observe. So, and it did it with a straight calculation and no dark matter. So the question is, well, if it just accidentally got it correct, correct is correct, we should be able to reverse engineer the code to find out what is the gravity equation. So we start with the original code that ChatGPT produced, and then on the left-hand side, we're going to recover the centripetal force formula. So we do that by reverse engineering things by squaring everything on both sides. So now we've got the v squared on the left-hand side. Then we want to multiply it by the mass of the thing that's orbiting. So this is like mass of, say, satellite. We multiply that by both sides. And then to recover the centripetal force formula, we have to divide everything by r. So here we have the centripetal force formula. And it's equal to this thing, which should be the gravity formula. So the correct gravity formula is this expression, which is mostly constants, and this expresses the exponentially decaying disk, ultimately divided by r. So the bottom line is that gravity in a disk galaxy is just proportional to 1 over the radius, not 1 over the radius squared, which is what the spherical gravity law would say. And interestingly enough, this is the same presumption made by modified gravity. But obviously, it can only be made for, say, a disk galaxy. And we do have some new data which supports this idea that gravity is 1 over r. In Sabine Hassenfelder's video, it demonstrates a new fatal problem with dark matter because recent data shows that the curve is flat, way, way past where dark matter should exist. I mean, this is flat to like forever. Dark matter cannot explain this new data because dark matter has to end somewhere, but these curves remain flat way past anywhere anyone could reasonably consider dark matter to still consist. And this new data does agree with, for example, the 1 over r gravity that MOND uses, modified gravity uses. And it also agrees with ChatGPT's flat curve, which can go on forever. So I would say that the only problem with MOND isn't that it needs to be a modification of gravity. Rather, you need to apply the correct application of Newton's universal gravity formula and not the spherical one. And this also kind of explains, one of the criticisms with MOND is like, well, how does gravity know whether it should be like 1 over r squared in, say, the solar system versus, 1 over r, which is out in the far reaches of the galaxy, But it doesn't need to do that. It actually has to rely on the geometry of the galaxy, whether it's spherical versus it's a disk. So what would be the correct way to apply the universal law of gravity? So if de Hilster in his original paper is correct, then if we apply the true universal law of gravitation to the disk galaxy and not use the spherical gravity shortcut, we should be able to predict the flat rotation curves for real galaxies. And I did find a few papers that attempted to actually do this. And these papers do recognize that a disk is not a sphere, and say, since that simplification is not valid in the disk, a numerical algorithm was developed for calculating the acceleration due to the centripetal force resulting from gravitational interaction with the rest of the disk at each distance. And this particular paper, used individual star data to plot things out. So you can see that this is the orange line of their calculated rotational curves, and you can see it's all bumpy because it is using individual star locations, I would imagine, in order to calculate the force of gravity rather than using any kind of simplification, which would result in just like a perfectly smooth line. So the thing is that we can see here that the line also ended up following pretty closely to the blue line, which is the observed. I mean, the only discrepancy we have here is that their calculation understated the velocity by a fair amount. But they did get the shape of the curve almost exactly the same. If you take this orange curve and you superimpose it right over this blue line, you'd see that they match up almost exactly. I mean, even matching these little differences in the curve, there's a little dip there, there's a little dip here. You can see those in this curve as well. So this would be pretty strong evidence that if you apply, like the original shell theorem did, which is to calculate each individual block of matter or star against every other star, and I think this is really the only way you can do it without cheating, that you will eventually extract out the observed gravitational rotation curve. So, I mean, that might seem kind of daunting that, theoretically you might take a picture of a galaxy, map out every single star in there, and map out every single bit of gas that you think is in there, and then calculate the universal law, which is just using the distance between star A and star B, calculate the sum of all the forces of all the 10,000 stars that are there. And if you did that, instead of trying to cheat by using calculus, you would find that you can recover the flat rotation curve. And really, we have computers, so there's really no reason why we couldn't just do the brute force explanation. And there is another paper here that I found, which said that this was calculated using a method developed by Carl Friedrich Gauss. He's a pretty famous guy, should know what he's doing, which modeled spiral galaxies as cylinders. And their quote is, I showed that once one considers the mass distribution in a spiral galaxy is disk-like, as supposed to being a spherical distribution, the observed rotation curve is readily recovered. So this plot they made is for the same galaxy in this picture, which is M33. And we can see that the orange line represents the observed orbital velocities, and the blue line, which almost exactly matches, it even predicts and matches the increase in orbital velocity as you get further out. It matches almost exactly. And once again, this is done without any presumption of dark matter. This is just merely the correct application of the universal gravity law as it would apply to a disk-shaped galaxy as opposed to a spherical one. Now, the math in here is much, much too complicated for me to either confirm or deny whether this is correct. But once again, these are attempts of people to specifically address this problem of using the spherical gravity law on disk-shaped galaxies. Now, another paper really, challenges the idea that the law of gravity is like this one thing, because the law of gravity actually changes greatly depending on if we are inside or outside of the mass. So this paper asserts that the force of gravity is basically straight linear if you're inside an object. So here's a picture of a mass. And if you are inside, anywhere inside here, that really the gravity is proportional to the radius. But if you're outside an object like this, where you're outside, here's all the mass, and here's the point you're outside, this is where 1 over r squared gravity applies. So there are actually two different formulas of gravity depending whether you are inside or outside. And actually Newton described both of these as different theorems in his Principia, right? So they're two distinct gravity formulas. But oddly enough, this paper also basically treated disks and spheres interchangeably, although I don't think that is necessarily true, as I did try and ask ChatGPT to come, I confronted ChatGPT about it using the spherical gravity law, and said, oh yes, that's correct, and then had it trying to recalculate it not using that assumption. And it comes up with these very complicated integrals, which are hard to understand. So, but I just want to try to motivate this idea that the force of gravity, its form can change radically depending on whether you are considering the point inside a mass or whether you're considering a point outside of a mass. And for disk galaxies, we are definitely in the case when we are inside the object of mass. And you just cannot simply, from some of the references I'm seeing, they literally say that, oh, well, the disk is substantially spherically symmetric, which is insane. No, a disk is not spherically symmetric, yet they say exactly that ridiculous statement that it is. So, that could perhaps indicate a source of the problem, that people just don't think that they're different. So this really brings up the question of, this would be just a pretty simple problem that astronomers should recognize. And, if you asked anybody, this is a quote from that same paper, saying that the thing you're right about, Kepler's third law, indeed doesn't apply to orbits of the stars within the Milky Way. Kepler's third law only works in a special case where the system is almost completely dominated by a single mass, for example, the sun in our solar system. But the mass of the Milky Way is much more spread out. So, Kepler and the spherical law of gravity really can't tell us anything, right? However, how can 10,000 professional scientists be wrong? So the thing that, is presented is that the physicists and astronomers aren't totally incompetent. And they point out that the evidence for dark matter also comes from other places other than the rotation curves of the galaxy. But it must be that they know about this, right? There's no doubt that people would say that disks and spheres are not the same thing, and that they must be using some other more complicated formula for coming up with their expected Newtonian rotational curves. But, really. Yeah, given that there have been billions of dollars that have been spent on dark matter searches, it would just be a complete embarrassment to the mainstream science community, if the hypothesis of this presentation is true, which is that everyone was just using the shortcut spherical gravitational formula instead of using the more general universal Newtonian gravity formula, which has no neat shortcut for a disk. And like I said, I tried to have ChatGPT, come up with the gravity formula, and it is a complete mess. So I just want to motivate that, whatever the formula is for a disk, it's nothing simple. It's not anything over r squared. Nothing like that. You have to, take the disk and integrate it and compensate for the exponential decrease in mass, and you have to figure out how far that mass goes out for, and blah 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 blah. It's very complicated. So, this is the mystery. So on one hand, no one would disagree that the spherical gravity law cannot be applied to a disk-shaped galaxy, but really, all the evidence I can find points to them doing exactly this, which is applying the spherical gravity. And so what's the giveaway that they're using the spherical gravity giveaway? I cannot, it's very hard to find the source of their Newtonian calculations. I did, in fact, find their modrot.c, which theoretically is the program that they use to calculate the Newtonian gravity in the papers that are purporting that there exists dark matter. And the calculations include both things which are integrals but also clearly the spherical gravity law of something divided by radius is clearly present. But really, the giveaway is actually the shape of the curve that they're reporting as the expected result. Because, if you ask ChatGPT just straight up, plot me the rotational galaxy curves, it will do the mainstream thing of using the spherical gravity law, and it will calculate a curve which looks like this. This is very characteristic of using this gravity times the mass enclosed by r divided by r. Whenever you see this formula, it means they're using the spherical gravity law. So just by looking at this shape here, and just by looking at the shape of the graph in here, I think I can pretty much conclude that they are using the spherical gravity law. That this paper, which comes up with this curve, must have been using the spherical gravity law, no matter how complex the program they use to come up with their Newtonian gravity law. And so it doesn't matter, say, how carefully or what method is used to, say, calculate the mass, because they'll use impressive algorithms to separate the galaxy into its central bulge and into its outside and into its gas. Yeah, those might all be perfectly accurate, but the second you plug in the mass you found enclosed by that radius into this formula, well, you've screwed up. So to conclude, this presentation is making the rather radical claim that dark matter doesn't exist for the purposes of justifying the observed galactic rotation curves. And this is largely due to the misapplication of the spherical gravity law, 1 over r squared, to disk-shaped galaxies. Now, to be clear, no other claims are being made for the other evidences for dark matter, such as the picture of the bullet cluster or the CMBR. However, that does not discount the main hypothesis that dark matter is not necessary for galactic rotation curves. And as I mentioned before, I find it incredibly hard to believe that all of the very knowledgeable astrophysicists could have possibly made this kind of very obvious mistake. So, I could be wrong. But I have several questions that should be answered, could be answered, that I couldn't find while doing research for this presentation. So primarily, so the first question is, can it be confirmed that the predicted gravity curves use this spherical gravitational law, which presumes that the force of gravity falls over 1 over r squared, which only applies in the case where you are outside that sphere of matter. And as I said, I tried to research this, and I couldn't pin this down. And it could be that, yeah, they might use some other super complicated integral Bessel formula thingamajobber, which is trying to compensate for the disk shape. But, somehow they still end up with the same problem, because when we apply it to the spherical gravity, we find out that there's no dark matter anomaly, which once again, no matter how they did it, which is still pointing definitely the finger at it, assuming that the galaxy is spherical, because that's the only place where it works. So the second question I have is on the 6 galaxies with no dark matter, and whether these actually do have spherical symmetry, because just looking at flat 2D pictures and graphs, it's kind of hard to say that thing's actually a spherical ball. You could be looking at a disk from the top down or something. It still might be flat, but I just like to have it confirmed from someone who might really know whether there is this strong correlation between no dark matter and spherical symmetry. The converse is, can you find me any spherically symmetric galaxy which does appear to have dark matter? If you found me just one of those, that would refute this entire hypothesis of this presentation. Although I'm betting that you'll never find one. Never, ever, ever will you find a spherically symmetric galaxy which has the dark matter anomaly in it. So the other question would be, is that if the wrong gravity formula is being used, if you just brute force calculated the force of gravity between every single star, as I had tried to mention before, by taking a picture of the galaxy, map every single star. I don't care if there's a million stars in there. Calculate the force of gravity between each and every one of those stars to a particular star, and then see if the rotation curve matches what is actually observed. I would have thought that the two papers that I found may have done that, but once again, those papers are so complex that I can neither confirm or deny that they did something like that. But a brute force calculation should be doable with modern computers. Now the other question is that like ChatGPT, which came up with the gravity in the disk generally being 1 over r, similar to MOND, or the modified gravity hypothesis, is that, if you do all these calculations, does it really end up that the gravity is 1 over r? And that's why the galaxy rotation curves are flat? This would be somewhat in line with the other paper, which kind of treated disks and spheres as basically being the same. That when you're inside a disk, that as you move outside, from the inside to the outside, you are just encompassing ever increasing layers of matter. And so, yeah, you would intuitively just think that the further out you go, the more mass is included, so that increases the force of gravity as you go outward. And some other references in these papers indicated that the amount of matter that's inside of a galaxy was purportedly goes up linearly with the distance away from the galaxy core, and it's like the non-visible galaxy, which just consists of, like, say, the hydrogen gas. That's like 187% of the total galaxy matter. So a lot of matter may exist in these as ordinary hydrogen gas that we can see, and not dark matter. And all that really needs to happen. That's all that needs to happen to have a flat galaxy curve. Is there still be a lot of matter in the form of gas outside of the visible area? So the other question is, if this hypothesis does in fact end up being wrong, then you still have to answer that question of why do these spherical galaxies not contain dark matter, right? You got 6 of them, right? Like I said, you could explain away maybe one of them, but all 6 would be difficult, and this is a big problem. And you should probably consider that maybe dark matter has something to do with the geometry of a galaxy, right? Even if you don't accept that you calculated the gravitational rotational curves wrong, you still have this interesting question of why is it spherical galaxies don't contain dark matter. And also, it's kind of mysterious that this whole question of, do you treat disks like spheres, just doesn't seem to be at all addressed in the current literature. You look at papers describing dark matter, and they don't mention this at all. It's just presumed that we've got the calculation of the rotational galaxy curves due to the matter correct, and that's that, right? Because once again, it's just difficult to believe that all astrophysicists, after spending billions of dollars, have seemingly missed what should have been an obvious mistake. So thank you for bearing with me on this rather long and extensive video. If you have any answers to the questions I pose, please feel free to contact me. My email is franklinhu@yahoo.com. And yes, I would really love to have you make some comments on this video, write me emails, send me hate mail if you don't like this. Also, if you're interested in my other theories, and yeah, as a dissident scientist, I have a number of very radical solutions to a number of science physics problems. You can find my videos on my YouTube channel at Franklin T. Who. You can also find all of my links to all of my materials on my website, which is franklinwho.com. So thank you, and please do comment.